I'll give everyone a second to join us. Welcome, everyone. You are joining us for Terahertz Time Domain Spectroscopy, the pulse-driving industrial innovation. This webinar is presented by Menlo Systems and hosted by us at Photonics Media. Today, you'll hear from Prince Bawuah, a product manager for Terahertz Systems at Menlo. He also serves as a part-time professor in Terahertz physics at the University of Eastern Finland. Prince obtained a Ph.D. in physics back in 2017. He's joined by Matthew Whittlesey, who is currently providing technical sales support for Menlo Systems. Matthew obtained his Ph.D. in 2022. Prince will explore practical applications in pharmaceutical manufacturing, semiconductor testing, coatings inspection, ceramics assessment, and EV battery electrode analysis, among with others with the assistance of Matthew. Before we begin, feel free to ask questions or leave comments in the chat box at any time. If you experience any technical problems during the event, please log out and rejoin. After the webinar, you'll be able to access the recording online and a link will be sent to your email. So with nothing further from me, I would like to welcome Prince Bawuah and Matthew Whittlesey.
Yeah, thank you very much, Ali, for the nice introduction. Yes, a moment, I will share my screen. Just a moment. I hope everyone can see my screen now. Okay, so let's go into it. Yeah. So today you'll be hearing more about terahertz and its applications in the industrial setting. Yes, so I'll give you a bit of context on why we need terahertz at this moment, and also some background of terahertz time domain spectroscopy, and then some current advancement in commercial terahertz systems. And then I will go into recent applications in industries, and we will have time to have some questions and answers, followed by some discussions. Yeah, a bit of Menlo. So Menlo, we are based in Munich, but then we are also found in the USA, China, and Japan. Yeah, we are into optical frequency combs and ultra-stable lasers, and also femtosecond fiber lasers. And as you can see, before you will get a good frequency comb, then you need to know the laser game. And if you are able to produce stable lasers, especially fiber femtosecond lasers, then terahertz is something you will be able to also do properly. So today we are going to concentrate on Menlo, our terahertz systems, and the solutions we have, and especially focus on industrial applications. Yeah, so we've been in the game for over 17 years now, and we were the first in Germany to sell commercial time domain systems. Yeah, so why terahertz now? As we all know, we are now in the world of AI with smart cities, driverless cars, and industries are also moving into smart manufacturing. And when we are talking about smart manufacturing, then it means that we should be able to really understand every unit in our processes. And to do so, we need tools that could help us to track every processes. And the end results will be to provide our customers with quality product cheaper, because the time we spend in the manufacturing will be lesser, and also we are going to avoid waste. So in this AI generated photo, you can see that we have robotic arms with terahertz sensors, and here the idea is to check the quality of your product in real time. So this is why terahertz as you will learn in a moment, have unique properties which could also support in this area or be a good complementary tool in this area. Yes, but before that, let's have a quick poll. And here we want to learn more about whether the industrialization or the applications of terahertz in industries are worth it. And we want to learn from you and also get your advice. Okay, so already I have an answer for that. We really believe that terahertz could aid in manufacturing. Yeah, about 85%. Yeah. Okay, the second posts are also coming in. Yeah, and I could see that it's been a tough choices here. Yeah. Okay, so for the second post, I think already we have 15% of the people going for continuous operation and also high scanning speed in order to meet the needs for industrial applications. Okay, the third poll. Mm-hmm. Okay, so here too, I'm having 36% going for electronics and semiconductor manufacturing, and then 18 going for pharmaceuticals and defense. Yeah. Okay. Thank you very much. And then I think we can continue with, yeah. Yeah. So then one will ask, what is this terahertz we are talking about? So when you look into the electromagnetic spectrum, terahertz lies between electronics and photonics. So which means that terahertz has some properties in both fields. So in terms of transparency, yeah, it behaves like the radio waves. So it penetrates and so many materials are semi-transparent in this area. And also in terms of transparency compared to X-ray, terahertz is transparent, but here we are talking about low energy levels. So in that case, you don't cause any harm to your samples. And you can also do spectroscopy. So about 0.1 to 10 terahertz is mostly very interesting range for terahertz. Yes. So when we consider the three states of matter, so in terms of gases, we are talking about molecular rotations. So terahertz could probe this type of bonds. And then in liquids, hydrogen bonding. And then in solid, we are talking about secondary dielectric relaxations and also crystalline phonons. So terahertz could probe this intermolecular movement. So in terms of the properties, as I've already mentioned, water absorbs a lot of this radiation, but then metals totally reflect the radiation. It is non-ionizing and it penetrates a lot of material. And then when you're dealing with powders, you can imagine that terahertz longer wavelength compared to the particle sizes, so less scattering, which means you can also penetrate, especially powders like products made from particles. Yeah. We have two main sources. We have the continuous wave, whereby here we are talking about like monochromatic terahertz wave frequency. So you may have a single frequency and then you can tune it. And typically you can do the tuning between 0.5 to 4 terahertz. And then we have the broadband one, which Menlo we provide our commercial systems based on the broadband systems. And here we are talking about 0.1 to 6 terahertz. So in terms of the continuous and the broadband, so with the continuous, it's just like dealing with X-rays or dealing with FTR spectroscopy. Here you are measuring intensities, but with the pulses, we are measuring the electric fields, so you have access to the complex optical constants. So you have both the real and the imaginary part of your optical properties. Yeah. And then the sources, there are various ways of generating terahertz. We have the quantum cascade lasers and then ionization of plasmas. And with this, you could even have even higher watts of terahertz radiation. But we are going for the optical generation. And in here, we have the nonlinear way, which is called the optical rectification, and then the photoconductive switches. But at Menlo, we are working with the photoconductive switches because it has several advantages. So it is more compact and eye safe because here you can pump your switches using fiber. And then it is cost effective, and you can also generate your terahertz signals at room temperature, and signal noise ratio is higher and also broadband. Yeah, so what happens during the generation of these terahertz pulses? So you have your photoconductive antenna, basically made up of gallium arsenide substrate, and then you have an antenna with a gap, and this is a femtosecond laser, which is capable of generating carriers here. So what happens? So you hit the band, and then you create your electron holes, and you can see that we have bias voltage here, and this bias accelerates these charges. And then the transient current which is created is what is called the terahertz. Yeah. So in our current systems, we've done a lot of modifications whereby we've increased the gap here. So you can now pump the antenna with the higher optical power. So what happens at the detection? Yeah. So the detecting material is also the same, similar, I would say. But here you have your femtosecond laser, which pumps the detector. You create carriers, but there is no bias voltage to drive these carriers. Now, these carriers are driven by the arriving terahertz pulses. So by delaying this, we could now scan or sample the electric field of these terahertz pulses. Yeah, and as you can see, if the femtosecond laser hits the antenna or the detector, it switches on, and if there is no pulse, it switches off. So this is time gated, and by means of time gating, we also get rid of background noises here. So this is a complete system, and this is how we do it at Menlo. So you have your femtosecond laser, and we really have a mode locking techniques we call figure 9, which is very stable. And here we don't use any saturable materials, which will degrade as time goes on. So you split your beam into two. So one goes into the emitter, and then one goes through the delay line to the detector. Yeah. Here with our new systems, we've upgraded the speed of our delay lines, and also we've increased the power of our emitters and then the detectors. And now we have a new amplifier. So you have your terahertz detected in the form of current, and these currents are very weak. So it goes through an amplifier which amplifies this and also convert it into voltage to be read by the computer. Yeah, and see that we've upgraded a lot in this area. Okay, so we've put all this into a very compact system we call the TerraSmart. So here you have your delay line, you have your lasers, you have your computer and the data acquisition card, everything inbuilt, the electronics here. So this is fully compact, ready for the industry and OEM customers. Yeah. You can also have multi-channel, whereby you will have two pairs of antennas. So you have two sets of experiments. So you can be running maybe transmission experiment at the same time, reflection experiment using a single engine. And this have enough power to probe two high power emitters and detectors at the same time. Yeah, you could also do pump probe experiments. You know more about pump probe, whereby you want to check some carrier dynamics. And then we have the most versatile one called the K15, and this is mostly meant for scientists to play around. So here you have a bit of high power lasers, but the terahertz performance is the same as that. But here you can also sync the laser with external laser. And also you have an additional 780 nanometer output of power. You can also do multi-channel. And these tools systems depends on the mechanical delay line. And now if we want to even go faster, whereby we get rid of the mechanical delay line, then comes the Tera OZ. So here we have two lasers inside this box, and these lasers are synced in such a way that we could track the time and also generate terahertz. So in this case, we don't have any moving stages. So we can scan very fast, and also we can scan very long. Yeah. Okay, good. Yeah, so these are the current performances. So in terms of power, the blue line is our previous performance and now our new performance. So you can see that in terms of power, we are now up to 3-4 times, like around 400 microwatt of terahertz power. And then we've also increased in dynamic range. So you can see that we can also do up to 110 dB with up to 6.5 terahertz. Yeah, and then having our new transimpedance amplifier, we do not have any form of saturation and the signals are clean. In terms of speed, yes, so this used to be, the blue line here used to be our performance. And now when you take the 50 scan range or length, you can see that this is the red line is now our new performance. So we are about 5 times faster now. And in terms of the competition, we are also about 2 times faster. These ones are fixed. So here with this, it is fixed. You cannot change the delay line, right? The scan length. Yeah, but with our systems, you can extend the scan range up to 1700 picosecond. And you can do this without any data stitching. So this is continuous scanning. Yeah. And the resolution is, if you can scan longer, which means that in frequency domain, you have a good resolution. Okay. So we have add-ons also for transmission and then reflection. So here you could see that this is our imaging stages and our transmission setup. So you could do transmission. And we have the reflection head for also reflection. And then comes the software. You cannot have a good hardware without a good software. So in terms of software, we have very flexible and user-friendly software. And when during gathering or during the measurement, you have softwares that will It will help you to set your experimental parameters and also do your measurement seamlessly. And then due to our impact in the terahertz market, even open sources takes into consideration our systems, and they build or they develop softwares which also work seamlessly with our systems. Good. Yeah, in terms of the imaging, we've upgraded and now we have new imaging systems with a new software which is fully integrated. So it is now much easier to interface, it is more flexible to mount, and also working and gathering data is very seamless. The analysis, we have the image lab, which is also one of its kind in the market, whereby you could also do a lot of analysis, whether in the time domain or frequency domain, depending on what you want to achieve. Yeah. And then for customized systems, as I mentioned, you can also do pump probes. So here you hit your sample with either of this, and now you measure what happens to the sample when they interact with this wavelength, with the terahertz. And as you can see here, we can do multicolor. And this is not even, we can even do more than this. We can do supercontinuum and also other wavelengths and frequencies. Yeah. Okay, now, so that is Menlo, how we've advanced the terahertz technology and how our new systems are performing. So now let's jump into the applications. So terahertz, as we all know, it's upcoming and people are trying it everywhere. So for thickness analysis, for food and pharma, so you see that I'll just highlight some of these applications where our systems have been used. So let's jump in straight. So this is in terms of terahertz applications, thickness analysis, especially in the automobile paint industry, is gaining traction nowadays. And as you can see here, there's a company called Das Nano, and they have fully integrated terahertz system. And this could be used in real time in checking the layers of painting of automobile industries. Yeah. And what is the importance of doing this? Yeah. For example, imagine that your car is not properly painted. This could lead to rust, and at the end of the day, it might cause them to repaint. So at the end of the day, if you are able to track the process inline, and with terahertz, this is non-invasive, so you can even use it on the wet paint, unlike ultrasound, whereby you need to touch the surface. Yes. So at the end of the day, you save material, you understand your process, you increase the number of cars you paint within a time, and at the end of the day, you make more profits, and also goods and products are also affordable for the ordinary people. Yeah. And even with our new improvement, now this is even getting even more, because now you could predict accurately because of speed, power, and also you could also scan faster because of our speeds. And another very important area is EV battery electrodes. So as you can see in this chart, so when you take the cost of a single dry cell or a battery, yeah, the cathode, which is the electrodes, take even more than half of the whole price. So which means that if you really understand the manufacturing process of these cathodes and or electrodes, and then the anodes, I would say, yeah, electrodes, then which means that you will be able to cut down costs and also make more profit. And normally this is how it is done. So we have the cathode, whereby we have the battery materials coated onto aluminum foil. And also we have the anode, whereby we coat these battery materials on the copper. And these are typical thicknesses. And with these thicknesses, although these materials absorb terahertz radiation, so we can go through given our recent performances. And the most important aspect here to check is the uniformity of the coated material in order to make sure that every cell delivers the exact amount of voltage it is meant to deliver. So for thickness and the porosity and conductivity, and this is terahertz. So terahertz, you can measure the thickness non-destructively or non-invasively. You can also know the porosity. So here there should be some spaces during charging and then discharging so that the ions, especially lithium ions, could fix themselves within the pores. Yeah. And when you have the optical constants, you have both the real and the imaginary part of the refractive index or the permittivity, then you can also translate into conductivity. Yeah. And there comes also the solid state batteries. So currently researchers at Lancaster are using our Terasma systems, and here they are checking the properties of solid state battery electrodes. So they are measuring the porosity and then the thicknesses of this. And not only batteries, also they are also working on hydrogen cells. And with hydrogen cells, normally you have this membrane somewhere which allows these charges to travel in between. And as time goes on, it gathers some amount of water. And terahertz, as I've already mentioned, is very sensitive to water. So terahertz has been used to monitor the states of water in these membranes. And now let's go to the plastic and the polymer world. So when you check our webpage in our application notes, we've done a lot on plastics. So in this figure, you can see that we are detecting delamination or defects in plastics. And these are artificially drilled holes and also metallic substances hidden somewhere. And using terahertz imaging, you could see clearly where these are. And then in another application notes, we work on trying to also find the percentage of fibers. So glass, sometimes you want to make these polymers a bit stronger. So you add some glass fibers. Yeah. And here you could see that depending on the percentages, terahertz imaging can also give a clear indication of how these fibers yes. And then before I go away from here, for paper manufacturing, terahertz has been used to check the dryness and also the smoothness or roughness of papers. And here you can see that with this node, we can get, using terahertz, you can get the variation of mass within a specific place. And I think last year, we also had this 20 euro note for the back page of photonic spectra. And one other interesting aspect dealing with terahertz in plastics is sorting. So mostly it is difficult to sort black plastics. And if you look around you, you could see that your computers or your chargers or your keyboards, many of these are black plastics. And normally this black material absorbs infrared radiation, which has been used to separate them or sort them. So by adding this black material, then you cannot use the conventional way. And terahertz has been the best way to sort this plastic because terahertz could permeate this black material. Yeah, and then in terms of cultural heritage and preservation, a moment here. Yeah, terahertz has also been used a lot in terms of art to assess and also to restore art. So by comparing terahertz to other radiations, you could see that with terahertz, we could penetrate even deeper. So you could know the various layers of a paint or art material. And then for sculptures and architectural art, we've also done some work with the University of Marburg. And here you could see that with terahertz too, you could also identify some hidden cracks. So you can track these echoes and know specifically where the crack is within. Yeah. But just using your visible photo, it is difficult to see these hidden cracks that terahertz will allow us to see inside. And then in food and agriculture, so terahertz has also been used in plants. So this is an image of a leaf, and this will also give you traces of water content on the leaf. So by so doing, you could also detect early diseases in plants. Yeah, and other research are even using ATR methods to check the health of plants. And in chestnut, other researchers have also used terahertz to assess the quality of chestnuts. And here you could see that with terahertz imaging, you could separate between healthy chestnuts and then the percentage of healthy and then, yeah. And also for identification of tree species. So here we have about 5 types of trees, and using the absorption frequency, absorption spectra, you could also differentiate between them. And another interesting research from Australia is seed infections in sheep farming. So as the sheep they roam around the grasses, normally these seeds gets into their wool and then go into on top of their skin, and as time goes on, it starts sinking into their skin, and this is a major issue. So here is a simulation whereby we have a wool with seeds and wool without, and using terahertz, you could actually see this. Okay, and then in egg also, like, yeah, also one of the interesting applications. So you know that terahertz could permeate the shell and also the membrane. So by doing terahertz analysis, we could also check the quality or the fertility or something like of eggs, and this will be quite interesting. Yeah. Now let's go into the electronics and then the semiconductors, and then here, using our pump probe methods, we could also pump a surface with high power visible light and then probe to see what is happening. So here we can check carrier dynamics and then realizations, and also this could also lead into the development of new electronics devices. And there is this terahertz near field optical microscopy. So with this, our OME customer called AutoCube, so they buy our Terahertz smart systems and then put it into their system. And what happens here is that you have your AFM tape here, and then you focus your terahertz on the tip and you measure the scattered light. So by so doing, you could form 2D images in the nanometer level. So here our resolution is now limited to the AFM tip. So here you could do nanometer level terahertz imaging. And as you can imagine, you could track defaults in computer chips, whereby very tiny structures are made on them. And then in the area of 6G, yeah, researchers in Cambridge are developing modulators using metamaterials whereby this modulates the polarization state of a terahertz radiation. And in Warwick, also building or printing multiplexing, like waveguides for terahertz multiplexing. So here you could see that we have an emitter, 2 emitters, 1 receiver, and each is sending different frequencies. And depending on how the waveguides are made, we can multiplex these signals. And this is the future of communication. And this is how our systems are also helping in developing this area. In the area of biomedicals, like a group in China is also using our TeraSmart system sitting in their lab, and now they are studying dental caries. So these are terahertz images, and through this they could study our teeth. Yeah. And then on the skin, a group in Warwick are also developing autonomous robots for real-time skin sensing. So imagine that you have some skin diseases, so you do reflection measurement, and then based on your data, which is in the form of impulses, you can also differentiate between a healthy and then a diseased skin. And yeah, these are some of the interesting. So now I want us to go a bit more into the pharma. I think I still have some time left here. Yes. So in the area of pharmaceutics, the drugs we take here. So these tablets we take when we are ill are made up of different powders, and they are grouped into two mainly, either the active ingredients or excipients. So these powders, before they are turned into tablet, they are mixed well, and then from there into the tableting machines. So, and in real world, these tableting machines are so huge that some of them even create 1 million of tablets within an hour. So at the end of the day, you have different types, different shapes of tablets with for different purposes. We have immediate release drugs like the painkillers we take normally you take, and then you want the drug to be released immediately. And then we have extended release drugs. So some of the tablets are coated, some are not coated. And at the end of the day, you need to check their release properties. And this is what we call the dissolution and then the disintegrating properties. So with the dissolution properties, we want to see how this drug will be released in terms of concentration. So you put your tablet in this bath, which simulates maybe the human body fluid, and then you check how the drugs are being released per minute or hours. And normally we have the pharmacopoeia, which has this time of release. And if this meets the pharmacopoeia, then you can go ahead to sell. But then if it fails, then you have to destroy the whole batch. Yeah. So, and this is what has been done for years. Yeah. But now using terahertz, we want to really understand. And when you take a drug, you can also a tablet, you can see that porosity plays a major role. And when we are talking about porosity, we mean that the amount of air volume or particles in the drug after compaction. Yeah, so a tablet with a higher porosity, in effect, will dissolve faster or break down faster than a tablet with a lower porosity. So that is why porosity is a major property which drives these release properties. And with terahertz, we are trying to just one moment, yeah. We are trying to find a way of detecting these porosities non-destructively. So you take a terahertz pulse through a tablet. So this is in the transmission, or you can also do in the reflection. And by capturing the transmitted or the reflected signal, we can get the refractive index and then convert it into porosity. So in this research, together with the University of Cambridge, using our reflection head, we just pan it around the tablet. And here, given the high power nature of our terahertz sources, we are using just a single terahertz pulse to detect the thickness and also the porosity. And as you can see, reflection, so which means that you can easily also incorporate this into the production line and also even use it on already packed or blister packed tablets. Yeah. 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 So by tracking the reflectance, so now using the delay one, we can get the thickness, and now using the delay two, we can get the refractive index or the porosity. So I will go a bit forward here and then let you know that we are not just tracking the porosity, also we want to also understand the mechanism of water ingression through the tablet. So you have your reflection head with the tablet, and then you dip it into the water, doing real-time analysis, and then we can track the waterfront here. So by tracking the waterfront, we will know the disintegration time, and also by tracking the first pulse, we can also check the swelling. Yeah. And this, together with models, will help us to understand our drugs. And if you understand the release properties of your drug during manufacturing, which means that the development time is reduced, you understand the process, and also the quality of your drugs are already defined in the process. And this is what is called quality by design in pharma. Yeah, and this will make drugs faster, cheaper, and everybody will have access to good drugs. Yeah, so from this work, recently our colleagues at Cambridge have published this article, and you can see that our Terasma system is sitting right in the center of their lab. And this is the reflection head. And using the high power terahertz sources, it is easier to extract your data. And then together with them, we did some research also here at Menlo, where initially, in order to get the porosity of the tablet, you have a laser which does the thickness measurement, and then this moves to the terahertz, then you do your terahertz. But then you can imagine that you have various steps and more errors. But with our new high power, this allows us to use a single terahertz source, and with a single terahertz source, we can track the thickness and also the porosity, as you can see here. And this manuscript has been accepted just this week by this journal. Yeah, so in summary, I would say that we have several benefits from terahertz wave, yeah, and this comes as a complementary to existing techniques like near infrared, mid infrared, Raman, X-rays, UV, visible, yeah, yeah. And the main composition of the terahertz is a laser. And when we're talking about a laser, you should have a good, very stable laser so that you don't destroy your antennas. And with the Menlo, our figure 9 mode locking systems, yeah, we have a very stable laser, and in that case, our antennas are safe. Yeah. Yeah. So applications I've taken you through. We have several applications, and what I've taken you through is just some recent, very recent applications where uh, our systems has been used. Yeah. So we provide the most compact and versatile, powerful systems, which is ready for the industry and also ready for OEM applications. Yeah. So before I go, I would like to remind you that next month we will have this laser world of photonics in Munich, and please, and as well as the world of quantum. So please do visit our booth B2, and then 407, and also for the quantum hall A, booth 526. So thank you for your time, and I think we still have some time for some discussions.
Thank you, Prince, for presenting. We now have time for a few questions before we wrap up. If you haven't already, please type your questions and comments into the webinar chat. Okay, it looks like the first question I have here. What is the current Menlo Systems market application distribution for the Terahertz apps? What are top 3 killer apps that are actually used daily in production?
That's a fairly good question, actually. So currently, we have been targeting, I guess target is the wrong word. The market kind of found us on this one, where terahertz has been fairly interesting, specifically with applications where other kind of technologies can't do the same thing as well, as was kind of answered in the poll. Price tends to be kind of an issue when it comes to terahertz technology. So when there's something that can't be done any other way, terahertz is a really cool way to do something non-destructively. Typically, those applications that we found are things such as Prince mentioned during our presentation, measuring porosity of pharmaceutical tablets so that you know how quickly they'll break down. That's a fairly difficult measurement to make otherwise, and a very slow one other than terahertz. Another very interesting one has been battery manufacturing, as it's been as they're being extruded, being able to in real time measure the um, conductivity, porosity, and thickness of the anode and cathode layers. And I was going to pick a third. A really interesting one we found has been looking at polymers as they are extruded and looking for defects and thicknesses and different material properties in those as they're being extruded out of a machine.
Great, thank you. Another question I have here is how effective or efficient, my apologies, is Terahertz technology for non-destructive testing of composite materials like glass fabric reinforced thermoplastics being used in automotive industries?
I have to confess I am not an expert in those materials, so I'm not 100% sure. From what I do know of glass fabric reinforced thermoplastics, my understanding is it's a polymer material where fibers are kind of used inside of it in order to strengthen that polymer. Um, I guess in terms of looking for defects in that, it would really depend on the defect size you'd be looking at. So typically when looking for defects or imperfections in a material, you're usually limited by the spot size of your terahertz beam at focus. Typically this is around 250 microns or so. So if you're kind of looking for specific spot defects in a material, generally with terahertz, this is kind of your spatial resolution. However, if you can find that kind of response, and as you can see here with the different degrees, you can see that we can see the different material compositions of the polymer in different segments, and you can also see that we scanned across millimeters there. However, the spatial resolution kind of sub-millimeter tends to get a little difficult. So depending on the defect size you're looking for inside of that material would be, I think, the biggest limiting factor.
Yeah.
But the
And then
material
Martin,
properties themselves seem very well suited to terahertz.
yes. And also to add to that, I think when you check our application notes, we've done some work before, I think with SKZ or Marburg, whereby we've studied this polymer orientations in these plastics. Yeah. So at the end of the day, Terahertz will give you an idea about how these glass fibers are oriented. And then if you know their orientation, then it will also give you an idea about their strength. Yeah.
Great. What is the depth resolution of terahertz on CaF2 crystal or common optically polished optical materials?
Assuming this is talking about depth in the z-axis, so penetrating into a material, generally this is actually a fairly difficult, and Prince, jump in if you feel free if I'm explaining this wrong, but that's a fairly difficult one actually to image. So because unlike optical microscopy where you might be looking at a two photon effect where you're only looking at focus, terahertz is interacting with the material as it focuses through the material and exits back out of the material. And because you're getting that interaction the whole way through the material, changing the z-axis through a material tends not to give great spatial resolution. Generally, terahertz performs best moving in 2 dimensions while staying at the focus of the beam. If you can orient your sample that way, it'll do very well. But beyond that, it can be a bit tricky to do that depth imaging in the z-axis.
Okay. Another question I have is, I work in nuclear fusion diagnostics. How your company covers terahertz tech for wavelength ranges of 40 to 150 micron, far infrared.
So actually, this kind of tends to be a spectral range that we at Menlo Systems really don't cover typically. So we typically work very well at the infrared wavelengths, typically starting at 1 micron or 1550, and then we'll get out about to mid-infrared, where we'll go from, say, 3 microns out to about 15, 18 microns. And then from there, we generally will generate terahertz by using, as Prince was presenting, photoconductive antennas, which generally covers this, thank you, this 100 gigahertz to 10 terahertz range.
Which
So 3 millimeters
corresponds,
to 30 microns. Oh, it does actually. I'm sorry. I had that a little off in my head. I thought that said, I'm sorry. I had that a little off. Yes. So generally our instruments will go up to about, and I'm doing this on the fly because I'm normally used to dealing in terahertz, is 6 terahertz. Prince, on the top of your head, do you know what that is in wavelength?
6 terahertz.
Yeah.
Yes, so 0.1 should be about 3. Like, it's not on the top of my head. Yeah, but then, like, so 1 should be about 30 microns. So maybe about around 200 microns somewhere. Yeah.
Okay.
So just real quick, so typically getting to those higher frequencies tends to be a bit difficult with the materials that we use. It's certainly possible. However, our standard instruments, it tends to be a bit tricky just due to trying to cover all of the wavelengths all at once. So kind of depending on your specific spectral range of interest, I guess feel free to reach out to us separately and I can give a more in-depth information.
Yes. So 10 microns is about 30, 10 terahertz is about 30 microns. So, yeah.
Okay. You mentioned terahertz could be used for gases, rotational, fire structure, etc. Oh, fine structure, my apologies. Does anyone have a practical application for gases that competes with lower cost instruments?
I'm Prince. Do you have a good
For
answer to this one?
gases,
Otherwise,
for gases, I don't remember have an experience. And also, I think in order to do gases, you also need a very high resolution. And then to do very high resolution, which means that you need to scan longer. Yes. Yeah, but then, I think I have not come across an applications whereby they've used our systems to do this. I need to check. Yeah.
Okay. And one final question. In the context of food safety, how does terahertz time domain spectroscopy facilitate the detection of foreign bodies in products like chocolate, and what are its limitations?
terahertz. So typically, when you're looking at something like food inspection, one really interesting thing to look at is actually the water content, and then as food goes bad, typically you'll get a slight material, the composition will slightly change, and because those the water as well as kind of living growth and that change tends to be very visible in terahertz. You'll get either a peak shift, a specific spectral feature will deepen, and usually for inspection reasons like that, you'll be able to find a key indicator that'll kind of be your quality metric, where then you can look at only that one feature and that kind of is the green light, yes, no. But what that feature is kind of strongly depends on what you're looking at, which is why I recommend seeing and testing it. I know we briefly touched on this, but Menlo does also offer test campaigns where if you do have a specific application or something you are interested in looking at, feel free to reach out and we can also take those samples and do a test with them and give those results back to you so that we can kind of see how effective the technology would be for your specific application.
Okay. Oh, go ahead, Prince.
Okay, so so for chocolate, as Matthew have already mentioned, so these are food samples, and normally it contains water. So I will think about maybe water will be maybe one of the most challenging aspects, whereby water absorbs a lot of this radiation. But also, given that now we've improved in power, so it is worth just checking. And also, if there are some impurities in the chocolate, we should see this through the optical constants, like the refractive index or the absorption. Yes.
Okay. If we haven't answered your question yet, please look out for a reply from us via email later. If you think of another question, feel free to email us at webinar@photonics.com. I'd like to thank our presenters one last time, Prince Bawuah and Matthew Whittlesey. And thank you all for participating in Terahertz Time Domain Spectroscopy, the pulse-driving industrial innovation. This event was presented by Menlo Systems and hosted by Photonics Media. Thank you all so much.
Yeah, thank you very much, and also everyone for your time. Yeah.
Thanks, everyone.